Hey guys, this is Mainak, your civil bro, and today we have brought another tutorial on Etabs. This is a building, a single story building, and it has a truss over it. And I've already designed the truss, roof truss. I'll give the link of that particular video to in the description. So now we'll design the main RCC structure for you. This is a single story building and the height of this is 3.6 meters. So I can share this PDF with you so that you can practice along with this these dimensions here. So I guess it will be easier for you to practice along with me there, because my main motive for you is to practice and learn, and if there is anything which I'm doing wrong, tell me that also. So that's the main motive, like, to learn together. So that's why practice along with me, and so that you can learn. Okay, so I have already prepared a build order also, so that to help me every time to remember the steps very in short. I can also share this with you, or I can take a screenshot, okay, if possible. Okay, so let's go. So the first thing which you want in Etabs is to just set the Etabs file, and let's do that. New model, and obviously we're going to make using our Indian codes. So let's do that. Use built-in settings, metric SI Indian code selected, click on OK, and obviously we're going to select the custom grid spacing here. So in Etabs, I'll try to make the tutorial in such a way so that if you are using Etabs for the first time, then also you will be able to do it. It's like some basic idea. Okay, so in Etabs, this is the x-axis. So this x-axis goes in this direction, and this is the y-axis. Okay, the vertical axis is the y-axis, and this is the x-axis. So if you are doing this x-axis like this, so you can use this dimensions of this grid lines here from here. Okay, so here A0, B, the distance is 4.06, which I've seen from the AutoCAD file, and which I'll also be sharing in the form of PDF with you. And the next grid for the columns is 5.24, so we'll just add 4.06 plus 5.24, enter. It will just automatically calculate that for me, and yeah, I don't need this. Let me just take a singular CAD file. Okay, next is 5.5, so is equals to 9.3 plus 5.5, enter, and we'll add another one, is equals to 14.8 plus, we'll see the value from the CAD file. Let's see that it is 3.8. Okay, and then it is done here, and click on enter. So this y, and remember in this y direction you can see that this starts from the bottom, like it starts from the left to right. In the case of x it is done, but in the y direction it starts from the bottom. So you will make sure that you take the dimensions here from the bottom, so everything is in detail. So let's go. Here we have 2.4. Where should I do this? Yes, this is 2.4, and we'll go below, is equals to 2.4 plus, I'll see the value in there. Okay, it is a 3.575. let's write 3.575. let's go here, and yes, and then we have the next detail. I have not taken the dimension here. Yes, so the next detail is 4.5 is equals to 5.975 plus, I forgot, 4.5, enter. It is 10.475. let's match with these grid line, 10.5. so there's something wrong. You have to check here. So this is 2.4. okay, this is 2.4. this is okay, obviously, and the next dimension should be 6, and it is, yeah, this is a mistake. I think this is the mistake where the mistake happened. So 2.4 plus 3. Oh, this dimension I forgot for taking, I did give that thing the mistake. So plus 3.6 it would be 2.4 plus 3.6, correct, is equals to 6 plus last dimension. What is last dimension? 4.5. It's 10.5, and it matches with the this. So this dimensioning is correct. There was a little mistake in this while taking this dimension. Okay, so no problem. So we solve this issue and we move ahead and click on OK. The grid line is solved. Now the story data. So we'll obviously go for the custom story data. We'll delete two, delete story. Okay, so base to keep minus 1.5 as the foundation height. So obviously this will be 1.5 here, and this height will be 1.5 here. Okay, so this will be this makes the plinth level 0. So there are various advantages of making the plinth level 0. We'll learn later, but for now just believe me, plinth level 0 has many advantages. So we'll take the plinth level as 0 always. Okay, so the foundation level is 1.5. Plinth beam level is 0, and then we have the singular story height, and we take it from the elevation here, which is 3.6 meter. Okay, 0.45 was the plinth height. If you want, you can add the plinth height in this as well. Okay, so if you want to add the plinth height in there also, like 1.95 and here 1.95. so 1.5 is the foundation height and 0.45 is the plinth height. So this makes this most perfectly done. Okay, so similar to none, 3.6 meter is the height, so we don't have any floors above it, so nothing is required. Just click on OK and they click on OK. So here our grid space will be ready, and you can see by default we have two windows which will open, at least in Windows Etabs 16 to 22. This is the option here. So I recommend you to save the file in this moment, because if you have anything, if any error occurs, sometimes you may lose the sizes. So save the file in your desired location. So I've chosen my location and save, given the file name, and then click on save to save the file from here. And now this is the build order. Basically you need to set the things here and add new material. Obviously just go for India, and we'll go first of all at the concrete material. We'll go on M25, as the M25 is the maximum thing which has been allocated in this project. So we'll click on OK, and we add another new material here. This time we'll add the rebar, and we'll use FE500 here. Okay, HYSD 500, and then click on OK. No need to check this because it's already set and good. So this is done. Definition of materials is done, but I recommend to double check this whether this is added, because sometimes if you don't click on OK, these things are not done. Frame sections, will go for concrete column here directly. We'll edit this concrete column. So we'll go for C300 cross 300, and we'll just change the grade of concrete to M25, and we'll just do this here, modify this property. And you know that the moment of inertia in should be taken as 0.7%, 70% for columns and 35% for beams. So I have a detailed PDF and document about the IS 1893, which is a seismic code in which all these criteria are given. I'll share the link with you in the description. You can check that out, all the important clauses which I'm using this. So this is also clause, and the reference of this clause is also given in that document. Okay, just check that out. Then click on OK. Modifiers, this is done, and 300 and 300 is the size of this particular column here. And a reinforcement also, you need to change the the grade of steel which we have created here, obviously, and we don't want to change anything else here. And similarly for the beams here. So by the way, if you're making a new beam property, then you have to just modify this thing for beam and column, but I'm just editing the already beam property which is present by default in Etabs, so that's why I don't have to do that. So now we just change the beam, the grade of concrete in the beam here, and the width of the beam we'll do this as 300, and the depth of the beam we do this as 400. So these beams will use both in the plinth as well as in the top to support the truss which it already made, and the link to that particular video will give in the description. So just don't worry about that. Property modifier, this is for the beams. So moment of inertia is 35%, taken as 35% in both the direction for the beams as per 1893/2016 part 1. And reinforcement, FE500, which you've just created the property, change that thing only, and we're good to go. So I've not changed the property name here, so I should do that. B300 cross 400 will be used for both my plinth beam as well as the roof beam. So beam and column has been set. So now what next is the spring properties. We're not doing that right now. Diaphragms you don't need really, because there will not be any slab. The roof truss and above it PPGL sheets will be used, so no need of these diaphragms or any slabs. Spandrel levels, we are not using any shear wall. Group definitions not required. Section cuts not there. Response spectrum, we need to do the response spectrum load. We'll provide it, don't worry about that. Mass source also will provide, but first of all we need to go to the load patterns and do this. So just correct me if I'm wrong. I'm putting all the other loads in the other dead load, like the load on the load of the walls on the beams, and the load floor finish load on the other dead, because with a self multiplied 0. So this method is not wrong, I definitely know that, but if anyone knows that whether we can include this in the dead load itself and not include any other particular load case for that, is it the correct procedure? Let me know. Okay, so in the other dead load we'll put all the other dead loads, and in the dead load obviously we'll have the default self weight of the structure. So that's it, that's the idea behind it. So basically we are now going for the wind load here, WL, and we'll just give the title wind load here, and we'll use the Indian code for the wind load here. So the wind load code, the latest version is available here as of the date of recording. This is the latest code here, but I'm using a slightly lower version for the seismic load to be updated. So the latest version is 1893/2016, but we don't have this in 2022 Etabs. You'll find this obviously. So I'll have to use the 1893/2002. Latest one is till date is 2016. So SLX will add this new load, and SLY will also add. So as per this building license seismic zone 5, as per the new code, you have to add seismic load in 3 directions. So we don't have any option to do that for the static load in Etabs. However, for the dynamic loads, we can make a way in which we can apply the seismic load in the vertical direction, that is the Z axis here. Okay, so then we'll just modify some of the loads. Dead load, live load is okay. Start from the wind load here, and here we can choose exposure from shell objects. If you just give the shells, or you can just do extent of diaphragms also, but this we don't have any diaphragms here, so this won't apply actually. So yeah, so we just do exposure from shell objects, I guess. Okay, but we have to apply the coefficient manually. We can choose a weight, a sheet. You can give a sheet without any weight and apply that only on that particular object. That would be good. Okay, so we'll see. So wind speed in this Tripura Agartala is 55, and training category is 1. And the bottom story, you always want to choose the plinth level as your bottom story here. Okay, seismic load, will modify the lateral load here. Just take the X here, and seismic zone factor, this is the zone factor for various zones. Our building is seismic zone 5, we'll choose this. So all these details you'll find in my document, in the document, not mine anymore, it's all yours, which I'll attach, and you can see that site type. This is for soft soil, this is medium soil, this is hard soil, medium soil, and soft soil. So we'll go with medium soil. You need a soil test report for that. I've already checked the soil test report for this particular file, and use the bottom story as the plinth level here, and then click on OK, and then do the same with the lateral load here, and then just do this and click on OK. So this is done, and then click on OK. So seismic load has been set here. So we go to define, and now go to our load cases. You can see these 3 load cases are present here. Okay, so now let me check the build order. So load pattern seismic load in 2 directions is given. Now we define the response spectrum function here. So define here, and this building is seismic zone 5, so by default you have to apply the response spectrum load here for any particular structure. There are various clauses. If structure has seismic zone 5 or 4, or if structure has large spans or like that, there are some clauses here. So we'll delete this spectrum, we'll add new function here. So wait, So we first of all you choose the code here. So our code is obviously is code here, is 2002, and add new function here, function obviously 1. Seismic zone factor for 5 is 0.36. It's okay, fine. So I'll type 2 and then click on just OK and click on OK. So we have added the function here, default function here. So after defining the function, we have to define the model case in risk factor for the acceleration in 3 direction here. So you go to define and define model cases and modify this, just modify this, make this as RIDS, and after playing RIDS here we do this as acceleration. So we are, since the structure is in seismic zone 5, so we apply the acceleration in the 3 directions. Okay, and click on OK. So number of modes you can modify. By default it is 12. So if this was a larger story building, we would increase that. By default you can, for thumb rule, you can just take the number of floors into 3. You can choose this as the number of modes here. For this building this will be sufficient. This is the single story building. Okay, and after that we have to add in, go to load case, and you have to response spectrum load in these 3 directions here. Okay, define and go to load cases, and we'll add a new load case here, and obviously this will be a response spectrum load, and this I'll do this RSX here, and acceleration U1, and scale factor. Scale factor I had already shown in the previous video. For the Indian code it is IG by twice of the R. I is the importance factor here. Okay, the importance factor for this particular building will be 1. So all this data you find in the document here. G is actually a small g, actually not the capital G to be exact. This is the acceleration due to gravity, which is 9.81 meter per second. 2 is 2, and R is the response direction factor, which is 5. So the denominator comes as 2 into 5, which is 10 here for this particular building. By the way, I is we have 3 I's in table number 10 of IS 1893-2016. So I is you have 1 for non-general buildings, 1.2 for buildings more than 200 occupancy, and for important structures such as hospitals, etc., you have 1.5. So I into G comes as 1 into 9.81 divided by 10. So it comes as 0.98. Okay, so the scale factor 1.98. But by the way, if you're using other codes like the American codes and all this is IG by R, not IG by 2R. So you can check in the CSI itself. You just search the scale for response spectrum in Etabs. It all will come. I've already shown in a video, so I don't want to show in this particular video, but you can just check. Okay, having that done, and keep this as CQC and SRSS by default. These 2 are mathematical procedures, and add copy of case. I'll do this. Okay, this will be RSY, and this will be just U2, and click on OK. Add copy of case. This will be RSZ, and this will be U3, and click on OK, and then click on OK. So this has been added here like this, and let's do the modeling here. So you can hover over to this and go to the plinth level here. Okay, plinth level is 0 obviously, and we'll choose the columns here. So quick draw columns and choose the column size from here. This is the column size 300 to 400, and we have the grids perfectly done here, and we can easily choose the columns here like this in the both of the 2 grids. We'll go to plinth level back, and then we'll choose the beams here. This is the quick draw secondary beams, and this is the quick draw beams columns, and we'll choose the beam property here, B 300 to 400, and we'll draw the beams here like this, and we'll go up and draw the roof beams also like this. Okay, so you can also see this in the extruded view. Okay, like this, very easy. So just go there and go to the bottommost story, click on escape to go to the normal cursor view. Select all this and go to assign and go to joint and go to restraints here, and use the fixed support and apply and OK. So this is done, and after this is done, it's time to apply the loads here. So we select these beams at the plinth level like this. So plinth level beams are selected, and we go to assign frame loads. So these are the loads of the walls which will be acting on the on the beams. Okay, So this will be frame loads, and this will be distributed, and you can easily calculate that using the calculator option. And here the height will be 3.6 minus 0.4, because the 0.4 is the beam width, so 3.2. So 3.2 into 0.25, let's take this as the wall thickness, and into the unit weight of brick, it is 20, so it comes as 16. So let's apply a load of 16 here. So instead we apply minus, but here it is not required since it is applying already in the gravity direction. Click on apply and click on OK. So this is done, and we'll choose the beams for the roof. Here, as we have seen in the previous video, we had created a roof truss. So this roof truss was for this building, the link which you'll also see in the description here below. So we are applying an approximate load of 5 kilonewton per meter square, which will be sufficient for the roof truss here. So assign frame loads and distributed, and the dead, and 5 kilonewton per meter square for the spans of the roof truss, which will go, and all the purlins and all the bottom cords and top cords. Just check the video out to see the members of the roof truss, and for that. So 5 will apply, and we'll click on OK. So there will be no floor here, so basically there won't be any live loads here. So we'll just define the mass source here. I'll just modify this, and basically this is dead load, but I'll just show you how to do this. So dead load, and a specific portion of the other dead load will also come, because both of these are dead load. And the live load, this will be, if this live load is more than 3, then 50%, or live load is less than 3, then 25%. This will come like this. Okay, addition element self mass, just ignore this element self mass, because already include the other dead load. Otherwise, if you don't add the self weight, then you need to click this. Okay, so simply click on OK, and then click on OK. So this is how we define the mass source of the structure. By the way, this is also included in the document, so I recommend you to check that out. And by the way, I can think and make a more detailed video on that particular thing. So let's apply a panel for defining the wind loads here. So since we have chosen the shell objects method, so we'll use this, draw this, and we'll use the property, make sure this is none, because we don't want to have any like loads for this particular thing. Okay, and make this property as none, so not quick draw wall, and this is the draw object here, property none, and this is the this option will be better, draw floor, wall, or plan. Okay, so select line and make sure this edge drawing type is straight line, and then it should be good. Okay, like this. So we'll apply the wind pressure coefficient CP here. You can rotate this, press shift button and the middle of your mouse button. Those who are playing computer games, they know how to handle software better, and also those who have experience in 3D and all, making 3D images in Lumion, SketchUp, so they already know, and also AutoCAD. Okay, so we select this all, and basically the coefficient will be different for the different directions. So I'll just apply one by one. Okay, so this is the x, positive x. So for the wind to act like this, it should be in the positive x direction. So let me just assign shell loads, wind pressure coefficient, wind load, windward side CP1, and click on apply. So this is in this direction, perfect here. So and in this particular direction here, so this, let it be the leeward, and click on apply. So this is going like this here, leeward, and if I want to apply this like this, so I'll just do -1 instead of this. Already placed this and apply here. Okay, select this again and apply. So it will be also in this particular direction. By the way, you can check the wind code for applying the wind load in the perfect direction. This is not the perfect one, but this is just an approximate method. Perfect one, if you are defining this one like this one should also be like this. So just saying, but this should this should become, the result should come by this method on the conservative side. So this is the positive y-axis. So select this windward side, flow 1, and click on apply. So it is coming like this. When it is coming like this, I want like this, so I'll do -1 to change the direction. So select this and then do that. So all the loads will be along the direction of this one. Leeward side, apply, and -1, yes, this is okay. This will be on this side. So yeah, this is done, and we'll go to define, and we'll go to define load combination, add new combo, not new combo, default combo. So there are some load combinations which you need to add here, as per the earthquake code. I'll figure a way to add this, because by default otherwise you have to add all this one by one using manually. So we'll see those later, which we can find in my documents. Okay, for now we'll just analyze this and see. And here I'll just run the analysis here to check, and then we'll run the this one. This is concrete frame design, so we'll run the concrete frame design. So and do this and verify all members passed. So all members have passed. So now I'll also show you how to calculate the reinforcement available. So in max, first of all, for all the columns, let's see in all the columns the reinforcement coming here is 720. Okay, 720 is the reinforcement. Now how to decide how to do this? So first of all, you need to know about the bar areas, right? Bar areas, yeah. So the basic formula for is the cross section formula, pi by 4 into d square. So for 16 it is 201, and for 3 it is 314, for 20 25 it is 490, 32 is 804. So minimum 4 bars have to be given in this this particular rebar. So how do you know that? We just go to define section properties, frame sections, and you just check this out. Okay, now how many maximum and minimum? So maximum are these number of bars, minimum we have 4 number of bars in the 4 corners. So if the bar area is coming as 720, and if we give the number of bars as 4 number of 12 bars, so is equals to 4 into 12, that is 1 on 3, it is coming as 452. So this is less than 470, so these won't do. But if we go do this, take the area of 16 mm rod, which is 4 into 800, and that this is sufficient. So 4 bars of 16 are sufficient in this particular single story building for all the columns, since in all the columns we have 720. But in actual, like if you have a bigger structure, some reinforcement might be different for different columns. So you have to check each and every columns individually to do that. And for the beams, let's see. For the beams, the maximum here we have this 406 is the maximum which I'm having here. And let's see, 406. I can also display this on a better scale. Like if I have this on this particular view, select this particular view and design this, like just to have a the view in this particular view. I can also have this. By the way, 406 is the maximum which I got here. This view is lot better to check the things out, right? So this is story 2. In this story 2, the maximum force 280, 300, let's say. Suppose 300 is the maximum one, and if you go below this particular story, 0, yeah, this 406 we have, which is the maximum. And obviously you can find this for less. Suppose for the top you have the more requirement at the ends, because the the moment is like this, more at the ends at the top, and at the center it is more for the bottom part. So like this. So usually want to keep the main reinforcement of the top and the bottom safe. Extra, if you want to provide extra bars, you can give more extra bars at the top. Okay, so 491, let's go 500, or let's go more safe, even 600. So if you want to apply 600, how many bars we need to give? So if we give 3 bars of 16, then it's 600. Okay, so if for columns we provide 4, 16, 5. Okay, 5 I cannot write, this I can write, but this is difficult, so I just use hash. Okay, 416 hash here, 416 5 rebars for the columns. Okay, this is for the columns. And for the beams, and column size is 300 into 300. Okay, this is the size of the columns, and beams, my size is 300 cross 400. okay, and the top rebar all through. I'm not providing any extra bars here, not required. Bottom, this is 316. If I provide 316, then it is 600, so I provide 316 fine at the top and at the bottom. So if I go exactly, so exactly if I go more economical, like 494 is the maximum, so if I can take like 500, if I go 500, then I can go like even you can go like 216, 216 plus 112 plus 112 5. You can even go this one, okay, I think so, because 216 is equals 2 into 16 plus 1 into 12. This comes around 515, the maximum bar required area, which is 494. So anyway, the section will pass. But if you want to go a little bit safer, then you can apply 416. Otherwise, I think you have this will be sufficient. So the beam reinforcement will be 216 plus 112 for both the all the beams, and the column requirement will be 416. So this is the and if you don't want to be more safe, you can just provide more 412. That's what I have provided in the actual project. This is the reinforcement, because always that is easy better to have some factor of safety here with the analysis, if the for the better safety of the structure. So that's why this is the column reinforcement, this is the beam reinforcement, and this is the total procedure for designing this particular. Just end this with the 3D view to display and undeformed shape. And let me just get rid of this, okay, just select this and this, and right click, and then hide selected objects, and this is my thumbnail actually. So extruded view, and so the full building is designed in Etabs. And check my other videos, and if you have any kind of doubts, make sure you write in the comment section. If you have seen anything which is applied wrong as per your view, also write in the comment section. I'm open to changes, open to improvement. Thanks to all of you guys for supporting me. Drop a like. Bye bye.